Swayam Prabha. Digital India. Educated India.
In this module, we are going to learn about two applications of perturbation theory of degenerate states in atomic systems, well atomic and molecular systems. But before that, let us just remember where we had stopped in the last module. We developed this first order perturbation theory for degenerate states. We understood that for degenerate states where you have n number of wave functions associated with the same unperturbed energy, where the size denote complete set of orthonormal functions, you cannot write the perturbed energies as perturbed wave functions as size 0th plus something. First of all, you need a linear combination because you do not know which of these functions is going to contribute in which perturbed wave function. They are all identical, indistinguishable. So, well functional forms may be different, but indistinguishable in the sense that energy is same. So, there is no way in which we can say that one particular wave function will contribute and the others will not, okay, cannot do that. So, this is what it is. We write the wave function, we start with a linear combination of wave function, then go to the usual definition of our corrected wave function, usual definition of corrected energy, and then we arrive at this matrix equation in which we see perturbation Vij operates on these eigenvectors to give the Ek first order energies as the diagonal elements of this matrix capital X. This is something I think I forgot to say earlier. This capital X is the matrix of first order corrections to energies. And here the beauty is you can see from this expression here that all the off diagonal elements are going to be 0, delta Ij, remember. So, we are going to have this diagonal matrix where the diagonal elements are only going to be non-zero and they are going to give you the values of first order corrections to energies. We start from here. The first system that we discuss is that of a non-rigid rotor, and there the perturbation that we have to consider is centrifugal distortion. We have already studied at length this unperturbed system of rigid rotors, and the assumption there was that the molecule is like a rod. It does not change bond length in the course of rotation, or the bond length is equal to the equilibrium bond length. In a non-rigid rotor, what happens is the bond is flexible, it is not like a rod. So, what happens if you take a spring, tie some weight at the end and rotate it? The spring is going to get elongated, right. So, we are still working within right now, we have not said whether Born-Oppenheimer approximation is valid or not, we are sort of working within it. We are not considering vibration and rotation simultaneously as such, but we are considering the effect of vibration, that the average value of R0 square, which is the all important term in the rigid rotor Hamiltonian, that average value of R0 square is going to increase. Okay. So, we start with the unperturbed system rigid rotor. For that the Hamiltonian, as we know, is L square by 2I. When L square by 2I operates on psi j 0th, we get B j into j plus 1. I was thinking that I am making some mistake somewhere and I have actually written it a little later also, sorry about that. Of course, I think you can see that this equation is not complete, you must write the wave function also. 0th order psi j. Okay. This is what we have learnt, and Ej 0th will be equal to then B into j plus 1, just this, nothing. So, perturbation is centrifugal distortion, as we said, somehow it came and vanished, is not it. From classical mechanics we know that the centrifugal distortion is associated with a potential that is proportional to the fourth order of angular momentum. So, we construct the operator V equal to k minus k L to the power 4. Now, please remember here we are going to use it, what L to the power 4 means. So, L square psi is equal to say something, what do I write? Let me write A psi. So, now if L square operates on this function, this is a function, right. L square operates on L square psi, what do I get? L square operating on A psi, A will come out, and L square operating on psi will give me, we had said A earlier. So, I get A square psi, right. Of course, you have done this in your tutorials and all. Left hand side will be L to the power 4 operating on psi. So, this is the meaning of L to the power 4, L square has to operate twice, that is all. But of course, you know it, in case there is a confusion in anybody's mind, I thought I will just say it once. Okay. So, this is your centrifugal distortion. So, centrifugal distortion when it operates on the wave function, and remember we will still work with the uncorrected 0th order wave function. There is no need to incorporate the correction term, as we have learned a few modules ago. We get minus k L to the power 4 operating on psi j 0th. Now, remembering that L square by 2I operating on psi j 0th gives me Bj into j plus 1, I can rewrite that and I can get L square operates on the uncorrected wave function to give me 2I multiplied by B multiplied by j into j plus 1 multiplied by psi j 0th. Now, what do I have to do to get this eigen value of L to the power 4? I have to make another L square operate here. So, when I do that, what do I get? 2IB, these are all constants, they come out, j into j plus 1 constant come out. So, I am left with all these constants multiplied by L square operating on psi j 0th, and I know that is going to give me, well, it is going to give me 2IB j into j plus 1 multiplied by psi j 0th, simple, right. So, we make this operation and we get V operating on psi j 0th is equal to minus k L to the power 4 operating on psi j 0th gives us minus 4 k I square b square j square into j plus 1 whole square psi j 0th. Please do not square psi, the wave function, okay. You need to understand how the operation is done, I am sure you are clear with that. Okay. So, this is what I get, this is the eigen value of this V operator. Okay. So, V operating on psi j 0th gives me, in short we will write minus d into j square into j plus 1 whole square psi j 0th, where d is equal to 4 k I square b square. Okay. Now, see, let us work with this wave function with this level j equal to 1, which is triply degenerate. You can work with any level. In fact, I will encourage you to work with j equal to 2 or something and see for yourself what happens. I mean, if you work with j equal to 0, that will be cheating, because there is no question of degeneracy there. So, let us work with this j equal to 1, which is triply degenerate, mj, for that the magnetic quantum number is equal to minus 1 0 plus 1. So, the V matrix, as we have discussed earlier, is going to be something like this. The matrix elements will be written V11, V12, V13 and so on and so forth. Our job is to find the matrix elements. Well, now if you remember the linear equations that we had written earlier, in order to get solutions there, the secular determinant has to be 0. This is something that is very well known, Cramer's rule. We are going to use it and maybe I will discuss a little more about that when we talk about variation theorem. So, secular determinant has to be equal to 0, that means the determinant corresponding to this matrix should be equal to 0. So, det V will be equal to 0, something like that, right, minus x. Okay. Now see, we will try to simplify these expressions for V11, V12 and so on and so forth. To do that, we will remember that the psi j 0th is really an eigenfunction of the operator V, and it has an eigenvalue minus d into j square into j plus 1 whole square. So, with that let us begin. We will also remember that this V and H 0th actually commute, right, it is apparent here, there is a common set of wave functions. So, what is VII? VII will be integral psi I 0th V psi I 0th over all space. Do we have VII here? Yeah, V11, V22, V33. What is the value? I can write like this, V operating on psi I 0th I know is minus d into j square into j plus 1 whole square, all that is your all that is constant. So, we will come outside the integral. Inside the integral you have integral psi I 0th multiplied by psi I 0th, well if it is complex then psi I 0th star multiplied by psi I 0th integrated over all space. What is that? We know what that is, is not it? We know that this is equal to 1. Great. So, already we have simplified and we have found the expressions for VII. So, the expression will be minus d into j square into j plus 1 whole square. So, you take this and Vij, what is Vij? So, basically we are going to replace this expression here, but before that let us think a little bit about Vij. Vij has two different wave functions, integral psi I 0th whole psi I 0th star multiplied by V operating on psi j 0th integrated over all space. That will give me similarly d, I have written j dash just to signify that this I and j are different, minus d j dash square multiplied by j dash plus 1 whole square multiplied by integral psi I 0th star psi j 0th over all space, and we know very well that these wave functions are orthonormal. So, this is going to be equal to 0. So, what we are saying is that Vij is equal to 0. Now, when I say I and j, what do I mean? It is very clear what I mean by VII. What do I mean when I say I and j? Well, not so difficult also. I mean that we are talking about two different degenerate wave functions. Okay. So, that is equal to 0. So, now the secular determinant, I will just show you that once again. So, remember all these diagonal terms will become this minus d into j square into j plus 1 whole square minus x. All of diagonal terms as we see here is going to become 0. So, this is the secular determinant, that is equal to 0, very simple, right. Take the determinant, this multiplied by this multiplied by this equal to 0. The expression that you get for x, which is the first order correction to energy, is minus d j square into j plus 1 whole square. It has 3 roots, but the 3 roots are identical, is not it? Because what we have essentially is minus d into j square into j plus 1 whole square minus x whole cube equal to 0. So, the roots are identical, roots are the same, and we have the same amount of correction to energy for centrifugal distortion no matter what L value we have chosen, well, no matter what M value we have chosen rather. Okay. So, this is the expression that we get. Ej now instead of Bj into j plus 1 becomes minus d, becomes Bj into j plus 1 minus dj square into j plus 1 whole square. So, this is a case where perturbation removes none of the degeneracies. Whatever degeneracy was there will remain, right. We have demonstrated this with this J equal to 1 state, which is triply degenerate. So, what we see is that energies will go up, but a term in M is not coming in. Okay. So, all the 3 M sub levels have gone up by the total energy by the same amount. The total energy has gone up by the same amount for all the 3 sub levels. This is an example of perturbation theoretical treatment of degenerate systems where degeneracy is not lifted at all, but do not think there is no effect. The energy is changing. Energy of each J level is decreased by dJ square into J plus 1 whole square. Okay. So much for our non-rigid rotor. But now we want to discuss something in which actually degeneracy is lifted, and that example is provided by Stark effect. Stark effect means lifting of degeneracy by electric field, and we are going to learn Stark effect. We are going to go a little quickly through this because we have actually introduced all the necessary tools. I really would like you to try and do things yourself. So, let us talk about the principal quantum number 2 for hydrogen atom now. I hope the change in gear was not very quick. We are talking about non-rigid rotor so far. Now, we are talking about Stark effect in hydrogen atom. Okay. N equal to 2. For n equal to 2, what are the orbitals? The first wave function is 2s, second one is 2p0, third one is 2p minus 1, fourth one is 2p plus 1. And once again, even though it might have become a cliche, please do not forget 2p minus 1 is neither 2px, neither not 2pz, not 2py, 2p plus 1 is neither 2px nor 2py, but rather a linear combination of them. 2px and 2py are obtained by linear combinations of this 2p minus 1 and 2p1 as well. 2pz is actually equal to 2p0. Okay, when m equal to 0, then we actually get the pz orbital. We have discussed this in significant detail while talking about orbitals. Okay. So, V in this case is minus equal to r, where E is the electric field, and we can write it as minus epsilon r cos theta, because it can be at an angle, right. So, that we can write as minus epsilon into z, where epsilon is the magnitude of the electric field. Now, this is a secular determinant that is equal to 0. Here it is important to remember what V12, V213 and all that is. Here we are designating 2s as 1. So, V11 would be the perturbation term involving 2s orbital and 2s orbital. Same with V22, V33, V44, fine. What about V12? It involves 2s orbital and 2p0 orbital. What is V13? It involves 2s orbital and your 2p minus 1 orbital and so on and so forth. Alright. Now, as usual, first let us write down the wave function. Actually, I should have written the theta phi part here as well, but anyway, to start with, theta is fine. So, this is the theta part of the wave function, as you know. And now I do not remember exactly if I have, we did talk about recursion relations, but I do not remember if I talked about this. If not, just take it axiomatically that when you take a, what kind of polynomials are these? Like where? No, Legendre. So, when a Legendre polynomial is multiplied by the coordinate, then you get a linear sum of the polynomial before and polynomial after. I think we did it, yes, recursion relation, we actually discussed it. Right. So, here our variable is cos theta. So, I have written cos theta multiplied by the Legendre polynomial in cos theta, and here I have written L because I am talking about hydrogen atoms. Sometimes by mistake I might have written J, please correct it when talking about hydrogen atoms. So, it is a linear sum of the polynomial in L minus 1 and polynomial in L plus 2. Okay. So, now what is your Vij? Vij is equal to minus epsilon r multiplied by pi cos theta pj cos theta integrated over all function space. Okay. Here we have our good friend cos theta multiplied by pj of cos theta. So, of course, you can expand using this recursion relation and you get minus epsilon r. I hope I have not missed brackets here. Minus epsilon r, no, there is no question, integral I can write PL of cos theta multiplied by A into PL minus 1 of cos theta plus B into PL plus 1 cos theta. Okay, so, naturally we get 2 terms and this gives me 0, right. Let us see. So, let us take these two. What do I get? I get something like integral PL of cos theta, well star of that if it is not real, actually it is real here, multiplied by PL minus 1 of cos theta, and this gives you something similar. This one is PL cos theta, second one is PL plus 1 in cos theta. Okay. So, I get 2 integrals and now see once again do not forget that these are wave functions, right, an orthonormal set. So, this integral PL in cos theta multiplied by PL minus 1 into cos theta integrated over all space, that has to be equal to 0, yeah, that must be equal to 0 because they are orthogonal to each other, same here. So, finally after all this you get the answer to be 0. Vij is equal to 0 unless your delta L equal to plus minus 1. What will happen if delta L is equal to plus minus 1? Delta L means the difference between I and j. If j equal to I plus 1 or if j equal to I minus 1, then one of these integrals is going to survive, right. So, if only if delta L equal to plus minus 1 we are going to get Vij non-zero, otherwise in all other cases you are going to get Vij equal to 0. Now let us think V11 that is 0, V22, V33, V44 very easily they are all equal to 0, you do not have to worry much, yeah, because of course delta L is not equal to plus minus 0 plus minus 1, it is plus minus 0. So, this V11, V22, V33, V44 are gone. What about V12? For V12 is delta L equal to 0, let us see, 1 means 2s, 2 means 2p0. So, of course, for this L equal to 0, for this L equal to, is it 0? Is it 1? Is it 1? Yeah? Yes, it is 1. Delta L is equal to 1. M here is 0, not L. Okay. Please do not get confused even if I try to confuse you. Okay. So, what we see is this 1 2 is going to be non-zero because delta L equal to plus minus 1. Similarly, V21 is also going to be non-zero because delta L equal to plus minus 1, right. In case I talk too much and confused you over the last 2 minutes, let me just say it once. We have proven that Vij is equal to 0 unless delta L equal to plus minus 1. For Vii, V11, V22, V33, V44, since delta L equal to 0, that is not plus minus 1, Vij, Vii is equal to 0. no problem. V12 and V21 are non-zero because delta L equal to plus minus 1. Okay. Here L is 0, here L is 1. In fact, since our time for this module is getting over, I leave it to you to work out and prove that V12 equal to V21 is equal to 3 epsilon. Remember what epsilon is? This is epsilon, magnitude of the electric field, not very difficult to work out. So, we get this kind of an expression. We will just go back here. What about V23? V23 means 2p0 and 2p minus 1 for both L equal to 1. So, delta L is 0 again. Same with V24, V43, V42, V32. For all these delta L equal to 0. So, all these are equal to 0. So, I have already told you what V12 and V21 are, the 3 epsilon, and I need to figure out what is V13, V14, V31, V41. For that, well, I have put the cart before the horse and I have shown you the answer first. So, even these are equal to 0. Why? Because now we need to worry about the we have to worry about the imaginary phi dependent part of the wave function also. And it is not very difficult to see that this Lz, of which this capital phi is an eigenfunction, and minus epsilon z, that is just z, they are going to have common eigenfunctions. So, by applying the logic that we have done already, we can establish that these are 0, and you can also figure out that x is equal to 0, 0, plus 3 and minus 3 in terms of epsilon. Okay. So, now what has happened? If x, what is x? X is the first order correction to energy. So, if that is equal to 0, that means there is no change in energy. So, what we see is that for these 4 orbitals S, P, 2s, 2p0, 2p minus 1, 2p plus 1, 2 of them do not change in energy. One is stabilized, one is destabilized. Okay. Which one will be stabilized, which one will be destabilized? Not very difficult to say that the one that is aligned with the electric field, the orbital whose angular momentum is aligned with the electric field will get stabilized. The one for which it is not aligned with the electric field, that will get destabilized. So, that has to be plus 1 and minus 1. Okay. So, let me just draw a schematic diagram. I request you to have a look at Pillar's book for a more detailed level diagram. Here I am just going to draw a little sketchy sketch, if I may call it that. Here we had these 4 orbitals, 2s, 2p0, 2p minus 1, 2p plus 1. Out of these 2 are stabilized and destabilized, and I have told you that one has one of them is 2p plus 1, one of them is 2p minus 1. I have told you the direction of angular momentum with respect to the electric field. Now I would like you to, it is very simple, figure out whether plus 1 is stabilized or minus 1. Very easy, most of you would have got the answer by the time I finish the question, but please do it. Sometimes it is better to ask oneself easy questions also. Now what I want to draw your attention to is that 2 orbitals do not change in energy. So out of these 2, which is S and which is P? 2s and 2p0, they do not change energy, right. For them your x is equal to 0. So here can I say that this one is 2s and that one is 2p? How will I do it? Because again energy is the same, so I cannot do it. So here I have to take linear combination. So I have to take something like C1, whatever it is, I will call it maybe C and D, I will not even write 1. So, I can write C, psi 2 zeroth plus d psi 1 0. There is no reason for writing 2 before 1, but then it does not really matter. So, these are actually linear combinations of this 2s and the 2p0 orbitals. Okay. How to find the coefficient, all that is easy, and suppose what I am saying is not even right. Suppose they are s orbital and p orbital, they do not combine, even then this is fine, because in that case one of the coefficients will be equal to 0. So, this is general expression, and now for the first time we have encountered the mixing of orbitals, right. When we write linear combination, what we are doing essentially is that we are saying that the orbitals have mixed. So, when orbitals mix, you get what are called hybrid orbitals. You are familiar with hybrid orbitals? We have learned earlier about hybrid orbitals in valence bond theory. So, here what are we doing? We are mixing 2s and 2p0, we are getting hybrid orbitals, okay. And in this case the two hybrid orbitals have the same energy, right. And we have discussed a situation in which perturbation removes some of the degeneracies, not all, not none, some. This plus 1 and minus 1 get very different energies, and the 2s and 2p0, these orbitals mix and the energy is not changed. That leads us to the concept of hybrid orbitals. This is the discussion of perturbation theory that I wanted to perform. So, the stage is set to go back to our multi-electron atoms if I only want to talk about perturbation theory, but there is another method that we want to learn, and that is variation method. That is what we will do, and then we will see how variation method and perturbation method both can be used to take us back to multi-electron atoms, and then we will discuss a little further. So, as you see, 41 lectures I think are over. It is supposed to be a 60 to 70 lecture course. So, about 2/3 of the course is over, and we are nowhere near molecules. That is because the tools that we develop while learning multi-electron atoms are very useful when you want to talk about molecular systems. We do want to talk about approximation methods that are typical of molecular systems as well, like Huckel method, but those are easy. These are more fundamental, more interesting, and requires a little more attention. That is why we are spending so much of time on learning these techniques. And before ending the module, let me also say this: it is impossible to understand this unless you go back and work out everything by yourself. Also, you should refer to books. See, I am typing all this on the slides, it is human to err. So, it is very possible that there will be error in the slides that I might not notice. So, it is important that you also read the book. Books also have typos, but well, to a lesser extent perhaps, or maybe mine is a lesser extent. So, please do read the books that we have referred to, and please do write it out. It is important to write out these things, then only you will understand. Okay? So, I trust that you will be able to do that, and next time we are going to talk about variation methods.